In this video, we're going to look at the current electricity section of the NotesQuest. At the start of the learning outcomes, and also we start off with the definitions section, which starts off with circuit symbols. For this, you just need to draw the circuit symbols for these ones here. You can just look them up. If you just search Google for, say, cell and circuit symbol, you'll just see an image and you just need to draw that into your book. The next section is about measuring current and voltage. In this section, you need to describe what a voltmeter and ammeter can be used for in a circuit. In this image, you can see a cell or battery here providing 12 volts and a bulb which has a resistance of 2 ohms. We'll talk about more of that in the future. But first of all, we want to know how we can measure the current and the voltage. These are two useful properties. The current can be measured using one of these, which is an ammeter, but they've got to be connected in series. That means in the flow of the circuit. So you can see the electrons are flowing around this way. Well, they're not actually, but that's how we use the arrows. We'll talk about that in a minute. And the voltmeter here, this measures the voltage, but this has got to be connected in parallel across the thing you want to measure. So say I want the voltage of this bulb. See how it's connected in parallel, and it's giving me a reading of 12 volts for that and 6 amps for that. So here you can see a circuit diagram of that circuit you just saw. Make sure you always draw it carefully and complete the lines. There's no gaps in the circuit. Again, the voltmeter is connected in parallel, and that measures the voltage, which has symbol V. The units, this is just a recap, are volts, again capital V. The ammeter, that needs to be connected in series, so that means in the circuit. It's measuring a flow, as we learned last time. Remember, current is a flow of electrons, the rate at which they flow. So how many electrons pass this point here per second. And this measures the current, which has units of amps, capital A. So that's current there. In addition, you need to know which direction the conventional current is. Now, the longer side of this here is the positive part of the terminal, and this side is the negative. You might have seen that when you've got batteries, there's a positive and negative side. So we say that the current, this is called conventional current, flows from positive to negative. That's shown here. Conventional current. That goes from positive to negative terminal. But actually, electrons are negative, and they're going to be repelled from this side and attracted towards the positive side. So the electrons actually go the other way. This is called the electron flow. And this goes from negative to positive terminal, going the opposite direction to conventional flow. You can see this addresses these three here. I'm talking about the resistance as well, which is this part here. If we think about it, in this circuit here, the ammeter must have no resistance. If it had resistance, it would block the flow, and there'll be no light lighting up. Whereas a voltmeter actually has infinite resistance. That means very large resistance. I can prove it to you because if I put that in its place, it's got such large resistance it stops all the electrons flowing and the light goes out. Whereas if I connect the ammeter in parallel and remove that and complete the wire here, you can see that it sets on fire. This is because the current flows around here and it goes down for the ammeter, which has no resistance, and back there and we get too much current. Too much current means a fire. Exciting. Then you've got a section on changing the current, which talks about what effect different things have on the flow of current. And we can see that if we go back to our animation here. Let's get rid of these and the wires and just have a nice simple circuit like this. I'm now going to fix this and the bulb lights up. Now, how can we affect the current? Let's put an ammeter in there. How can we produce more current? Well, one way we could do this is by increasing the voltage here. So if I click on my cell and change the voltage to, say, 14, and accept, you can see now the current's gone up to 7 amps. More voltage, more push of electrons, we're going to have more flow. The other thing we could do, well, let's see what happens if we play around with the resistance of the bulb. So if we drop the resistance of the bulb, say to 1 ohm, so we've halving the resistance, you can see actually the current gets so large that we set fire. So there's less resistance, there's going to be more current. You can see if I change resistance to 5 ohms and fix that, you can see we're getting much less current. If we now double that to 10 ohms, so ohms is the unit of resistance, you can see the current goes down even further. So that's what that talks about there, and you've just got to copy it on there. For resistance, we need to know what the symbol is, the unit, and also the symbol for the unit. So resistance is kind of a measure of how much sort of obstruction there is to the flow of electrons. And we use the symbol R to represent resistance. The units, which I do like, a cool one, they're called ohms, and they have the Greek symbol omega, which looks like that. And then it starts to talk about power. Now, we've talked about power previously. That's the rate at which energy is transferred. Okay, and we did that when we ran up the stairs. So in this case, if we think of the power of, say, a bulb, this is going to be the amount of energy we get per second. So amount, that would be light and heat in the case of a bulb, amount of energy per second. It's a rate. The symbol for power, remember, is P, and the units named after the Scottish scientist are watts. Symbol W. That covers these bits here, but then there is also an equation for power which we need to know. So, we learned an equation in the last topic. That was, remember, power was the amount of work done or energy transferred per second. So we could use that equation, but there's also a good one which involves current and voltage, which we now know how to measure. And that's why it's useful sometimes to measure it. Power is equal to current times voltage. So P equals IV. Some people remember it as poison IV, which is that plant. It tells you the equation P equals I times V. So if we, say, had a bulb set up like this, and we measure the current, and it's 2 amps, and the voltage, and let's say that's 4 volts, then to work out the power of the bulb, we use the equation P equals IV. Remember, I is current, that's the symbol for current, and V is voltage. Put the numbers in. P equals the current, which is up here, 2 amps, times by the voltage, which is there, 4. So we get an answer of 8 watts. So that tells me that that bulb is giving off 8 watts, let's use my funky pen, of light and heat. Sorry, 8 watts, 8 joules per second of light and heat. That's the power of that bulb. A kettle, on the other hand, would be much higher power because it gives off a lot more energy. The next part, sample calculations, gets you to do some examples, and you need to copy this blue part into your book. This is the first example, and it's a bit like the one I just did. If a lamp is connected to a 1.5 volt battery or cell, and the current is 2 amps, what's the power? Well, remember, you times the voltage by the current, or the current by the voltage, doesn't matter which way around you do it, and that gives you an answer of 3 watts. What we'd like you to do here is come up with your own examples for the other ones. So the 12 volt, which is like a car battery, and the 240 volts, which is like your house. So you could, for example, say a car battery has a 12 volt supply, and the current flowing through it is 2 amps. What would be the power? And then you could just do the calculation like it is here. So I'll leave you to do that one. Just going to talk briefly about the problem-solving questions. Remember, you need to have a go at these. I'm not going to give you the answers, but I'll guide you in the right direction. The first 2 examples are here, and you can just copy those down, talking about how power is different. I want you to come up with 2 more examples of real-life situations where one object is more power compared to a similar object. So the light bulb here, maybe you can think of another device, maybe a kettle or something, and just remember that the power is related by that equation P equals IV. So think of some other example, a kettle maybe. Oh, we've still got the funky pen. This is cool. Let's go back to black. Kettle. Think about what its voltage is and its current. And then you could compare that to, say, something else. So a kettle has actually got a very high power rating compared to, say, a something small, like a small lamp or something, because the kettles give out a lot more energy per second. You can also think of examples when we're running up the stairs. That's kind of like the example 1. Also lifting up weights. Okay, remember, power is the amount of energy used per second. So if you lift these up quicker, so if T is small, you're going to be more powerful than someone who lifts that up slower. You're using more energy per second. So running uses a lot more energy per second than walking. This one, draw a simple series circuit using appropriate circuit symbols, which include a battery, a bulb, a switch, a voltmeter, and ammeter. Remember to connect the voltmeter and ammeter correctly. So you can refer back to the one we did earlier, but remember you're going to start with a battery, and then you're going to have wires going round to those components. Remember, you've got the voltmeter, that has to be in parallel to the thing that you want to measure, and the ammeter, that has to be connected in series, which means inflow, in the flow. So it would be somewhere over here maybe, it could be here, it could be here, it could be here, as long as it's in series and not in parallel. Question 3 asks you to draw a parallel circuit using the proper circuit symbols, which has a battery, 2 bulbs, 2 switches, and a voltmeter. We want to be able to control each bulb separately. I'm going to talk a bit about this one because this one is actually an interesting circuit, similar to what we have in your house, which will help you answer this question. Here's the power supply, or the battery. Obviously in your house it's not a battery, it's something bigger than that. I'm going to put a bulb on one branch here and a bulb on a second branch here. This makes it a parallel circuit. So if I connect that up now, like this, we've got a nice parallel circuit. But we want to control each bulb separately. So you need to think about where you're going to put your switches so that you can switch them on separately. For example, if I put a switch here, which looks like that, then this, when it's open, is going to break the circuit. No electrons can flow at all, so both bulbs would come out. That's like a master switch. But if I want to control these separately, I need to think about where that switch is going to go. Don't forget to also include a voltmeter and an ammeter connected correctly. Wrong one there. You don't want to see my emails. Not as fun as this physics. The later ones ask you to think of a model. Okay, and there's some links there to help you with that. I'll let you have a think about that. Remember, often in class, if we haven't done it, we will do it. I'll use you to model the electrons. You'll walk around the room and you'll collect marbles to represent the energy. So you can think of models like that in there. So there's a couple of questions here about models to think of and how you can model, say, resistance there. That's for you to have a think about, and I'll leave that with you. That's the end of the section. Remember, the key things you need to know are written up here. And by the time you finish this NotesQuest, you'll have notes on all of those. Now, if you're stuck, give it a really good go. If you're still stuck, just drop me an email. I'm more than happy to help or rewatch the part of this video. Thank you for watching. Keep up the hard work.